Okay. Okay, so let me just check. You can see the screen, right?
Yes.
No,
Okay.
no.
So
Yeah, we can see the screen. The screen is not visible. Only you are visible.
I'm not visible. I'm visible. Screen is not visible.
Yeah.
Oh, so you cannot see the screen which shows that ice edge in the past.
No, no, no.
Oh, what is the problem? Let me check. Then I need to present entire screen. I think that would work.
Yes. Yes. Now you are visible.
I mean, that is not important. The screen is visible, right? The ice edge
Yeah.
is in the past.
Yeah. Screen is visible. Screen is
Okay,
Yes.
so I need to somehow write this. Okay, like this. Right. Right. Okay, so I think for this week we have some discussions about the ice ages, how the ice ages came, what are the causes responsible for them, and how to mathematically get some idea about the ice ages, about those topics. So we will discuss a bit of that, and I think assignment the problems related to ice ages were also there. So we will try to do some nearby problems which are close to the given assignment. I think, have you seen the assignment? So what are the problems in the assignment? I think one problem was on the ice edge. Another, I mean, five problems were on the ice edge, and other five problems were some stochastic resonance type of thing. So these two parts were there in this assignment. So anyways, we will try to simply the questions were simple. You will be basically be able to answer all those things, but we will try to understand some basic concepts of that. Okay. So okay, now the first question comes that how do you know whether ice ages happened in the past? What are the evidences of ice ages in the past? Of course, we refer to the paleoclimate data, but what are the uh, markers which confirm that there were ice ages or places were covered with ice? Now, so the first point here we have mentioned is the glaciers formed U-shaped or steep sloped walls with white flat floor. So there are certain regions, especially in the mid latitudes, where you will see different valleys of this type, this shape. And this type of valleys are generally not formed due to rivers. I mean, the valleys which are shaped by rivers are a little bit different, but this valleys which are affected by ice generally is more, let's say, U type, or the bottom is quite wide. This type of valleys are formed due to let's say this picture, the glacier is flowing through that valley. That's why it causes a lot of erosion, and due to that, it makes this type of valley. This is a schematic of the valley produced by the glaciers. Now there is another effect which is also known as it is called as erratic stone. So some stone which is not uh, which doesn't belong to the stones of the other class in a certain area must have come from somewhere else, and that can only be traveled. That can only be traveled by or carried by the glaciers, because rivers, of course, rivers can carry some type of stones, but in a large area or very big chunk of stones cannot be carried by rivers. It must be carried by glaciers, which has a higher carrying capacity, of course. So the fragments of rock debris that were transported by the glaciers, and they called the erratic stones. That is the second proof that ice ages did exist. And if we just go for some calculation or estimation of the age, then we will get at what time it occurred. Uh, these are some instances. And there were drillings into the ice cores. We already have read that in the past, in the especially areas of Greenland and Antarctica. These areas are chosen because still till date these areas have ice cores. So the ice cores are actually uh, compressed across a thick layer in those areas. So we can say a stratigraphy, we can see the evolution of ice uh, layers with respect to time, because the oldest ice will be at the bottom. So, and they also carry different isotopes, and which we analyze, we will get the temperatures. Let's say we will find the isotope ratio of oxygen, delta 18, that is the ratio of 16, O16 and O18, with comparison to some particular standard. So they are analyzed to estimate the temperature of the past. Also, there were living beings, animals and plants, which slowly adapted to colder climate, and that, of course, don't exist now. For example, I can think of a mammoth, the big elephant-like animal, which existed in the Ice Age, but it doesn't exist today. And there were also plants which adapted in order to prevent themselves from heavy ice or colder temperatures. So they also show evidences of lower temperatures in the past. And another point is the rebound of the surface uh, after the removal of the ice sheets. So large ice sheets, if there is a large weight, of course the surface will be curved due to the weight of huge weight of the ice sheets. And due to warming, the ice sheets will be removed, and actually our ground or the ground, the materials which constitute the ground is quite elastic. So after the removal of the ice, they will try to retain their original position. So they have started going upward, or that is called rebounding. Uh, that is still active in the areas like North America and the Eurasian region, North Europe, and some parts of Britain, and some parts of South America, that is called Patagonia, and also in Antarctica. So these are some evidences that as they're slowly and constantly rising from the bottom, there must be something which had suppressed them in the past, and as a restoring force, restoring mechanism, they are now rebounding to their original height or normal height. So these are some evidences that ice ages did exist in the past. And from those information, the paleontologists, the geologists, they also calculated the time period for um, different ice ages when the ice density was high or the ice extent was high, that type of evidences. So, okay, this picture is actually, yeah, I will just delete it. So just, okay, so before going to this picture, I will just ask if there is any doubt about the ice ages in the past. So the points, are they making sense, or do you want me to clarify some points about the ice ages?
It's fine.
Okay, so then Ankit, Mukesh, is it fine? These are very basic points actually, and not a lot of things to elaborate. So I will go to the next slide. Just an evidence, or just a small illustration of if you just keep finger on the honey or any viscous material, you will keep some mark of that. And after a finger is removed, it will try to be normal in a few seconds. So similar things happen with the glaciers. The glaciers are there across the land, then it will suppress the land. After the glaciers are removed, then the land will start growing upward, and they will try to be back to their normal position. So that is the action of rebound. That is the action which also known as the principle of isostasis. Okay, I have to open this up. Okay, so now going to the causes of ice ages. There are a few points mentioned as the causes of ice ages. So uh, I would like your participation about some of those points. So the first point was about carbonate silicate cycle. There's a changes in the compositions of atmosphere. So how do you think that might affect the ice ages or the temperature of the earth? So, so Arjun, you can start this point.
I think that carbon dioxide will be released in the atmosphere or absorbed
Hmm.
by the ocean.
Okay,
So that way it might regulate the amount of carbon dioxide.
so that might control the greenhouse effect, right?
Yeah,
So that is one thing. And also, it will also depend on the amount of vegetation in the land, because vegetations generally, I mean, the plants generally absorb the carbon dioxide and store it as carbons. So that technically reduces the greenhouse effect. Another effect is for silicate. For silicate, the case, do you have any guess about the silicate?
silicate is found in the land, right? Ground, rocks.
Yeah, I mean, that is found in the rocks, but for volcanic eruptions, they are also present as aerosols in the,
Okay.
especially in the stratosphere. So yeah, of course, our land, the crust, and I think, uh, yeah, crust and some part of mantle also has a lot of silicon, that is silicate, silicon plus oxide, silicon dioxide.
It cool down the atmosphere.
Yes, so
So
if it is present in the upper troposphere or stratosphere, then what will do it is it will try to reflect the sunlight more. If it is reflecting the sunlight more, it is essentially decreasing the amount which is reaching the ground or increasing the albedo. Now,
yeah,
you know about the albedo feedback. If albedo is higher, then the temperature will be lower because
lower. Yeah.
S by 4, S0 by 4 times 1 minus alpha, where alpha is the albedo, is absorbed by the atmosphere or the ground. I mean, something like that. I'm not going to the details, but that was the equation. So in that way, it has actually changed the compositions in the past. And also another effect is there. If the temperature is higher, I mean, our Earth and climate system and also oceanic system is a very complicated system. So if the temperature is higher, then solubility of carbon dioxide into the ocean also decreases. That is another effect. So, but if the carbon dioxide is higher, then the growth of the plants also increases. So it is a very complicated phenomenon.
Feedback. Is there a feedback over here?
Yes, yes, that is feedback. Feedback. Whatever is internally happening is the feedback. If some volcanic eruption is happening, then you cannot consider it as feedback. You should consider it as forcing.
Awesome.
Some, let's say, I mean, that is one sudden event, volcanic eruption. So you can consider it as forcing, but in response to that forcing, whatever will happen is the feedback.
Mm.
Anyways, Earth has managed well enough to balance all those internal interactions, and our temperatures have been kept stable till long. Now, the human forcing, it is not able to bear the human forcing. That's why the temperature is steadily increasing due to the carbon dioxide, because it is not a part of nature,
Absolutely.
artificial
Right.
material. Okay, so now there is another point: continent ocean configuration, development of mountains, and changes in the atmospheric and oceanic circulations. So, yeah, of course, I mean, whatever we are talking, if we want to talk in the sense of just giving an argument, there might be very uh, a lot of complications because it is not a simple system. In models, what people do is in models, there are certain parameters prescribed. They change certain parameters, let's say volcanic eruption, amount of CO2, amount of methane, and then they see the effect because it is not possible to guess by mind or do by hand. That's why the model answer is the best accepted answer. But we try to give some explanation in order to you know,
See the
understand the system.
direction.
Yeah, I mean, with some basic idea. But truly speaking, in most of the cases, the basic ideas will not work properly. That's why we have to do the modeling, and that's why people are spending so much money in building these complicated models. But still, I mean, as a science enthusiast, we try to understand in terms of the basic concepts. So, I would like to ask. Ocean continent configuration and development of mountains. So, how do you think from intuition that it might cause in the ice age or it can decrease the temperature? Because the total energy absorbed by the earth is constant, but still, how this configuration can change the, the beginning of the ice age or removal of the ice age, those type of things. So, actually, it is, I mean, not a straightforward answer and it requires complicated modeling. But we can see, we can, I mean, from a layman's point of view, we can say that uh, if the Earth is of symmetric composition, where land and oceans are distributed symmetrically, then the
Albedo.
temperature variations, those things will be very uniform, at least in the zonal direction. It will be uniform. But if somewhere land is higher, ocean is lower, somewhere land is lower, ocean is higher,
So actually, so albedo will be different, is it? For land and
well,
sea.
albedo will be different, but there is a catch. Let's say, I'm telling you, let's say you put a lot of land uniformly throughout the earth, then
Okay.
uh, actually the earth, there will not be a lot of chance for earth to develop desert type of thing. Okay. Because if it is mostly surrounded by oceans, then there will be very minimal chance that a place will get very less rainfall. Now, for deserts, let's say the rain has to be dried up, that things matter. That's why hardly any island is deserted, except from Australia. It is a very big island, that's why it has deserts. But that will change the albedo. Now, if you have a vast piece of continent in the middle of the earth, then the effective albedo will be different from the current configuration, which has, let's say, America in one part and Europe, Asia, and Africa in another part. So I think the effective albedo will be changed essentially. So that is one cause. Another cause is the wind circulation. The presence of land will change the wind circulation. And if the wind circulation is there, changes of wind circulations are there, then it can trigger a mechanism of ice. It can trigger or it can remove. Both are possible of ice accumulation. Now, if ice accumulation starts, then there is a problem. Then the ice albedo feedback is actually positive because if ice increases, then the albedo will also increase. That will cool down the planet. Then it will lead to an ice age. That is so. Of course, they require modeling, but the basic notion is this. Of course, this cause is very simple to understand the changes of the solar irradiance or luminosity. If it decreases, then we are more prone to enter an ice age. If it increases, then more we are more inclined towards having ice-free land. In fact, the luminosity of sun is actually increasing day by day. In the earlier time when sun was just formed, then the luminosity was quite low. Now it has increased. It is increasing actually, but it cannot account for the global warming. Maybe after one, I think I saw in some YouTube shorts or video that after 1 billion years, Earth will not be habitable due to the only cause of luminosity increase. So due to that, the temperature will be increased by five
Right.
degrees or that thing I saw somewhere.
Okay.
Okay, so now, I mean, it is actually simpler to understand because it is an external factor and it is not that complicated. Now, despite the complication that occurs in the Earth, scientist called named Milanković. So he tried to describe the uh, period of ice ages using a few factors. So Some of those factors include uh, eccentricity of the orbit, tilt of the Earth's axis, and precision of Earth. So, do you have an idea? Let me just check for a minute here. Okay. So, uh, what is eccentricity? Do you know?
Eccentricity is basically the shape of the orbit around the sun, right? If it is one, it is a circle. If it is greater than one, it is
Parabola.
an ellipse. If it is
Hyperbola.
greater than, yeah, parabola, hyperbola, yeah.
Right. So here, actually, according to Kepler's first law, all the orbits are elliptical. Okay. And that depends on the shape, depends on the eccentricity. If eccentricity is zero, then it is a perfect circle. If eccentricity is one, then I think it is a parabola. If eccentricity is between zero and one, then it is an ellipse. Okay. So I think Mercury has Mercury has the
Circular.
highest eccentricity till now. Pluto,
The lowest, right? Because it is circular, right?
no,
Mercury is,
Mercury is not circular. Mercury is the closest planet, right?
yeah, the orbit is circular.
I don't think
I
so.
am not
Let
sure.
me just check.
Okay. I'm
Just check.
not also sure.
I think Pluto had the highest eccentricity, but it is not a planet anymore. So eccentricity of planets, orbital eccentricity. Must be table. Yeah, so just note that circular orbit E equals to 0, elliptic E less than 1, of course E greater than 0. Parabola is E equals to 1 and hyperbolic trajectory is E greater than 1. So parabola, hyperbola are not closed systems. So if they reach hyperbola or parabola, they will not never come to the Earth, I mean the solar system again. So forget about those things. These two are of our interest.
I think like if comets are going, then they will, if they are
See,
circling the,
comets are, I mean, very complicated in terms of trajectory. There are two types of comets. Let's say Halley's comet. You have Halley's comet, you know. So Halley's
yeah,
comet,
but it is the nearest one, right? That
yes,
has
and it
reached.
repeats every 75 years, 76 years.
Okay.
So the trajectory is extremely elliptical for Halley's comet, and uh, but it is not parabolic. I think for the other comet, which only can travel once in their whole
It
lifetime,
will escape the Earth. I
that will
mean,
be
the sun, the solar system.
yes. That will be sorry, parabolic trajectory. Actually, it is a scattering problem in physics. Actually, equating the kinetic energy, potential energy, and finding the minimum distance, and from there finding the trajectory. It is a scattering problem, and I think the trajectory is parabolic for the comets, which only. I mean, of course, it is an attractive force also. The gravitational force is always attractive. Using those concepts, they try to derive the distance or the trajectories of different objects, and then they decide whether something will be parabolic, elliptic, or circular. That is the common.
Okay.
Yeah. So they have also mentioned, Wikipedia mentions more things. So 1 by r square. So
Oh,
for
yeah.
gravitational force, it will be minus 1 by r square. Some constant is, of course. For it is, I mean, a lot of things. If you start, you will be lost here. So yeah. So Milanković tried to uh, derive the time period for ice age using those things. And tilt of Earth axis. The second factor is tilt of Earth's axis. It is very simple, right? We have 23.5 degrees tilt now, but it is also not constant. It sometimes goes to 21 degree and sometimes goes to 24.5 degree, like that. The precision thing, that is quite new, because we are very familiar with the tilt of Earth axis since our childhood. But for precision, we don't know much about this. Do you have an idea of what precision is?
Precision is when the direction of the uh, direction of the axis of the Earth rotates, right? Rotates around,
Around the vertical axis, right?
yeah, the vertical axis. Yes.
Yeah. So basically, if you think of a conical section of a cone, it will remain in the cone or the surface of the cone. but
Angle will be the same. I
yes,
mean,
yes, the
tilt will
angle will be the central angle will be the same, or the I think it is called half angle or whatever. So it will be the same, but the direction will change. So let's say now it is here. So we have the pole star just uh, connecting that line to the pole star, which is a straight line. After a few years, that will be changed. So the our new pole star will be something else, some other star. So that's how the
okay.
precision works. So it has a less value of the time period. But yeah, these are the factors which affect the climate change in a long time period. But there are complications. We will conclude today's session with the complications, of course. So yes, so here is a more detailed quantification of those things. Eccentricity uh, varies in a cycle of 1 lakh years, or it is also called 100,000 years. So yeah, 1 lakh years. So sometimes it becomes more circular, sometimes it becomes more elliptic, and the change of circular to elliptic and then circular, that time period is 1 lakh years.
But
The
the eccentricity will vary between 0 and 1.
eccentricity will not vary between 0 and 1.
Oh, it is elliptical. Okay, okay, okay.
It is
Okay.
always elliptical. So I don't know whether they have let's say eccentricity is now 0.0167, which is nearly circular. Oh, yeah, we were about to talk about the Mercury. So Mercury has the greatest orbital eccentricity of any planet in the solar system. Okay, 0.2056. Anyways, that's fine. For Earth, I think eccentricity of it varies actually. Eccentricity of Earth that varies between some values. Uh, I forgot the values actually. Uh, let's check whether this, but it is always elliptical, but very slightly elliptical. It is not that it is sometimes circular, sometimes.
Actually, if it's between 0 and 1, it will be elliptical, right? According
No, no,
to
it is
the.
always elliptical. So let's say sometimes it is 0.16, sometimes it is 0.17, like that. The small variations happen.
Oh, okay.
Actually, circle is always a special, also a special kind of ellipse. You can say that whose semi-major and semi-minor axes are equal.
Equal, yeah.
So, anyways, so that thing will uh, change the total amount of solar radiation we see. So that is why eccentricity is important. Because of higher eccentricity, one place will stay longer, uh, which is farther from sun, and once one at one position, the planet will pass faster. If it is closer to sun, then it will travel faster. If it is farther from sun, it will pass slower. Due to that cause, now we are in the northern hemisphere, so our summer is actually slower. So we get more summer days compared to the winter days, and southern hemisphere gets more winter days compared to summer days. Let's say 6 or 7 days more.
Mm.
And obliquity, that is basically the axial tilt, 22.1 to 24.5. So it is, we know, because we have been learning from the childhood that due to the axial tilt, the northern hemisphere and the changes of daylight cycle, these things happen, right? So winter, summer, and daylight, amount of daylight, amount of night, darkness, these things vary. So if it was not there, then if it were not there, then the things will be very even. So there won't be any season changes. But due to that, it is there. And if it is increasing, if it increases somehow, then the season change will also be drastic. And it follows a 41,000 year cycle. Now, precision, as you mentioned, which is the wobbling of Earth, that is a movement of the Earth's axis in a cone, very similar to if you put a top and rotate it on the table or ground, it will wobble. Uh, so the actual angle is mostly the same, and that time period is 21,000 years. That is the least time period. Now, it is also seen that the eccentricity change doesn't have much impact on the climate change. It has, but it is less. Uh, but axial tilt and precision, they affect the climate more. Okay. The reason being, northern hemisphere has more land fraction compared to the southern hemisphere. So if due to some reason the northern hemisphere gets more sunlight or more solar energy, then the ice will be melted. Ice cores or ice sheets will be melted, and that might lead to deglaciation. If the opposite happens, if it somehow gets more less energy, then the ice sheets will start building slowly, and that will eventually lead to glaciation or ice age kind of situation. Uh, that's why Milanković actually argued about the heterogeneity between land and ocean in both the surfaces, and then he considered that these things will have effects. Otherwise, let's say if Earth was completely uh, even or uniform, completely land or completely ocean, then these effects won't be that permanent. Whatever uh, was there could last for long, but due to the heterogeneity, these things happen. I will mention about the summer cooling. So higher tilt can cause extreme changes of season. The distance of the summer or winter hemisphere from the sun influences the climate. Now about the summer cooling. If northern hemisphere, let's say, is colder in the summer, then what is the normal nature of summer? It tries to melt the ice cores or ice sheets. Now, if it is colder than usual, then in the summer, the ice sheets will not melt much. And of course, you can argue that the winter also be milder, but in the winter, they will anyhow grow. And if in winter it grows, then by the next year, the ice sheets will have a greater extent compared to the previous year. And this slow effect will eventually lead to ice age because at one point of time, the ice albedo feedback will take over, and that will support strongly the growth of the ice sheets. That will lead to ice age. There are barriers, there are threshold barriers, but Milanković actually described like this, that in the northern hemisphere, it will start and it will slowly grow in the northern hemisphere. Eventually, the whole of the world is connected via ocean circulation or atmospheric circulation. So it will affect the other regions also. So that was his main argument about the initiation of the ice age. Now, uh, though there are discrepancies in the data or there are some um, criticism of that thing. But at that point of time, considering no computers, no modeling, no availability of very good amount of quality data, he did a brilliant job at that point of time. So we identified those things, and we will also see that some periods exactly match with his calculation of this periodicity of the ice ages. So here is a picture about easy understanding of the. But before that, I will just go if someone is here. Oh, someone. No one is here apart from Arjun. Fine. See. Okay. So that is a Milanković cycle. So the eccentricity 1 lakh years to 4 lakh 13,000 years. Precision is 19,000 to 24,000 years. They are not exact numbers. Oh, so they have given example of a top. It is rotating, it changes its direction of the axis. And now finally the tilting, which has a time period of 41,000 years. So 21.5 to 24.5. Actually, it is currently decreasing 23.5. So we might experience milder weather or milder climate in the future, but it is also predicted by that we are actually heading towards an ice age. And some says it is 1000, some say it is 2000. We don't know when it will occur, but anyways, we have messed up with the uh, global warming, so the possibility of
Global warming will delay ice age, is it?
it is delayed. That's why it is delayed, and we don't know exactly when the ice age will come. Okay, then okay, so here is the about the power. So the precession cycle of 21,000 years, that has the highest power, and the obliquity cycle 41,000 years. That has second highest, and the eccentricity has the third. I mean, third has actually it is the lowest. It has very small power. But the ice age is from the past Paleoclimate. It occurs. The ice ages occur in the interval of 10 to the power 5 years time. So why it doesn't occur in the highest power cycle, which has a time period of 21,000 years? It has been mystery, and it is also paradoxical out of our own common intuition. Now, the answer to that is the fact is Earth is not a linear system. Suppose you are oscillating a wire at some frequency, uh, let's say one per second, 1 hertz, okay? Then the wire will also oscillate at 1 hertz per second because it is a linear system. But Earth is not a linear system. Suppose the wire is connected to some spring mass system, and the spring mass system is connected to some compressible fluid. This type of things, if there are complications, then the periodicity will not follow exactly whatever you are giving. So there comes the nonlinear effect. Similar things happen for the Earth also. That's why, due to the maybe internal feedback, internal
What do
mechanisms,
you
the
mean by
highest powers.
power actually?
Huh?
Highest power. What does the power mean actually? Is it the frequency? How does power mean? Highest power?
Okay, okay. So in time frequency time series analysis, actually what they do is they try to break the time series into summation of sines and cosines. So any
Okay.
periodic function, you know about Fourier transform. So any periodic, do you know about Fourier transform?
I think it's basically integral of e raised to f of x into
Okay,
some
that is the
function.
formula, that's fine, but what is the basic concept?
Okay, I don't know the.
So if you take any periodic function,
Okay.
because sine and cos functions, they are actually orthogonal. It means sine 0 is 0, but cos 0
Yeah.
is 1, sine
Yeah.
90 is 1, cos 90 is 0. So they are
Zero.
out of phase.
Yeah.
So if you take any periodic function, then it can be expressed as summation over sines and cosines. Okay.
Okay. Okay.
Now, not everything has a single time period. There are things which have composites or additions of different time periods. Suppose a function is y equals to sine x plus 2 times cos 2x plus 3 times cos maybe half x. So it has three different periods, but it is still periodic. After a certain time, it will repeat. Now,
Can you? My internet connection just went out. Can you just please repeat what you said?
okay, so let's say you take any periodic function. Okay,
Okay.
now the periodic function, uh, let me search on the internet actually. I just uh, Fourier transform images. If it is better to like understand in terms of images. Ah, let's just take. Okay. Let's just take this. Okay, is it clear? You can see the picture, right?
Yes. Yes.
Ah, so you don't need to concentrate on the formula, but just let's say it is a periodic function, very ugly looking function, but periodic.
Okay.
Now, due to the periodicity of the sine and cosine, because they will also meet the time period, at certain time point of time, they will again come to their original value. I mean the initial value. So it can be
Okay.
expressed as summation of cosines and sines. Now,
Okay.
let's say a function is actually summation over a cos omega t plus b sin omega t. But there are also other frequencies. So let's say there is omega 1, then a1 cos omega 1 plus a2 cos omega 2, this type of things. Okay.
Okay. Like precision, obliquity, and eccentricities.
Yes, you can think that.
How different?
I'm talking in mathematical sense, but you can relate
Okay.
to art sense. That's fine. So if you can add those things, you will get back the original function. Okay.
Okay.
Now,
Okay.
if the original function matches most with one of those terms, then you can say it has more power. Because let's say you have a function which varies yearly, which has 1 year time period, but it also varies daily. Let's say the temperature. Let's say the temperature is some particular temperature, let's say at your place, it is now 25 degrees Celsius. After 1 year, it will also be very close to 25 degrees Celsius and it will follow mostly the solar insolation. Okay, that is a
Yes.
very strong cycle. But in between, there will be occurrences of rainfall. Let's say one day might be foggy, one day there might be storm. These are small fluctuations, but their effect will be less. The most prominent effect will be your
What
during
I'm saying.
year. So the solar insolation. So in that case, you can say the power of the frequency corresponding to our solar insolation or 1 year cycle is the highest. So if you
Okay.
decompose in terms of different terms, then whatever factor is in front of them, in front of the cosine or sine factor, is the amplitude. The square
Okay.
of the amplitude is known as the power.
Okay. Okay. Okay.
In order to be, why it is squared? Because in Fourier transform, you can see that I still have the image of this. Yeah. So if you see those things, there are e to the power minus j omega t, right? That is a complex factor. So your power can also be complex. That's why they have taken the square absolute value
Oh,
such that you can express it into a single number, which
I disappears.
yes. So you can express it in terms of real numbers. Okay. Because of course our everything is, I mean, whatever we're experiencing at the end of the day, maybe we're using very complicated mathematical tricks, but it is real, right? We should get it some realistic, get some real value of that. That's why
Yeah.
we are squared, and that is the power. Okay.
Okay.
Okay, so in terms of power, you can think in a simple way that whatever cycle dominates, it has the highest power. Okay.
Okay. Okay.
Or in terms of mathematics, whatever coefficient is the highest has the highest power.
Okay. Thank you. Thank you.
Okay, so now, yes, so it is not a linear system. Despite giving powers of 21,000, I mean, more occurrences of 21,000 and 41,000 year cycle, it somehow ends up giving more power in the 10 to the power 5 cycle or 1 lakh years time period. At least it happened in the last 0.9 million years. Now, in the last 2.75 to 0.9 million years, that was more, I mean, well-behaved ice age, that were more behaved ice ages. So the cycles of uh, 41,000 and 23,000, actually it can be 21,000 or, I mean, just fine, it's 20 to 25,000. So these show stronger powers, okay.
Okay.
And so we cannot explain it exactly, at least for the last 0.9 million years in terms of the solar radiation variation that is due to the Milanković cycle. So you need to invoke something else to explain those things. Now, the response to the forcing might be sensitive to the internal conditions of the Earth. That is the nonlinearity comes in. That's how. That this can explain the longer period for ice age. One very popular theory is that it must come down below a threshold value for initiation of the ice age. Suppose it is showing periodicity, it is having a local minima, but the local minima is not low enough to start the ice albedo feedback. So there is a threshold value. That's why I think sir explained quite well, professor explained quite well
Yes.
in the lecture. So it might be local minima, but it is not coming down below a threshold value. So that fails. That is a failed case of ice age. Might be local temperature minima is there, but not an ice age. And so in that way, let's say one period is missed. So one, two, or more than that periods are missed. Next, so the next occurrence is after 1 lakh years or so. That is one explanation. Another explanation is using stochastic forcing. That is a mathematical thing. We will also try to do some mathematics on that. Now, uh, depending on the conditions of the Earth, ice age might or might, that's fine. Um, yeah, I think Earth has seen both completely snow-covered Earth and completely snow-free Earth. Both extremes were seen by the Earth. So now we are very stable. Now destabilizing ourselves, that is a different story, but we have seen both extremes past. I just added it. It's back the Milanković cycle just to show. Um, I think epsilon is one is for this. It is for the axial tilt, that is the axial angle, obliquity we call. This E is for the eccentricity. that is slowly varying 1 lakh years. Uh, the third one, which is quite fast varying, it is the precision, sine omega. When multiplied by, okay, so the eccentricity has actually some effect on this precision, because if eccentricity is there, it is highly eccentric, then the sine omega factor, or the direction of the summer hemisphere or the winter hemisphere, in which way it is directed, will also be more effective. In the present case, what is the date of the summer? I mean, what is the uh, okay? What is the date of highest solar irradiance in the northern hemisphere? What is the longest day on northern hemisphere? Can you just
When the northern hemisphere will be pointing to
yes,
the
yes, that is
sun.
true. What is the date roughly? Date or month?
It will be
What?
summer.
Yes, summer, of course. Which month? So basically, when the northern hemisphere summer happens, when the temperature is highest in your region, what is the month of the year?
Yeah.
Is it
Uh,
June, July, whatever?
Actually, the thing is, the temperature at my place is always high.
Oh, okay, okay, okay.
So,
Oh, so are you close to equator?
yeah, I'm from Kerala.
Okay,
So,
southern part of Kerala.
yeah, southern part of, no, not the south, middle part of Kerala.
Okay, close to Ernakulam.
Yeah.
Okay, okay. Yeah, so the highest actually insolation happens in the month of June. So 21st June is the longest day on the northern hemisphere. But also the distance of the sun is from the earth is highest close to that. That is actually, it is in 4th July. The distance is high. So if it is distant, it is higher by distance, the earth will move slowly. That's why in the summertime, the speed of the earth, orbital speed of earth is lower. So it moves slowly. Now it will also gather more sunlight. But what I want to point out is, if the eccentricity is there, then if it was circle, then it would not be a problem. The velocity will be always equal. For circle, it is
Okay.
always equal. For ellipse, it varies. That's why the ellipticity is multiplied with the factor of sine omega. That's why they work together. And together multiplying, you can see some changes in the time series. It has developed some new frequencies. Okay.
Okay.
And there's some new time periodicity is there. Let's say this follow this one. This is a longer time period. Okay. And if you just consider, it is almost 5. Yeah, just a longer time period. It has some it has developed some envelope. Anyways, now the third case is for the uh, benthic forums and Vostok ice core. You can see their periodicity is close to 100 kiloyears. That is 1 lakh years. That is the periodicity of the ice age. This cannot explain. This cannot explain. Uh, this somehow explains, because this distance is close to 1 millimeter, but this and this, they have higher powers. Anyways, so the nonlinear effect comes to cause the changes in the temperature with 100 kiloyears time period, or 1 lakh years time period. So that was the main takeaway for this Milanković cycle. So all the cycles, all the periodicities are graphically plotted here, and together with that, we have the data for ice core temperature. It's the temperature of Earth.
Okay.
That's that's just an easy, simple example. Just a simple example. Okay, the next slide is about Milanković cycle and climate change. So why is it is not a part of the Milanković cycle? I mean, many can argue, at least from the trends, they can argue that okay, it is the natural variation, the temperature of Earth can naturally vary. So why won't it be the natural variation or the Milanković part of Milanković cycle, which causes the climate, not climate change, the temperature increase? But scientists have well studied the past movements of Earth, orbital movements, precession, obliquity. And from there, they are actually predicting slow decrease of temperature this time. In fact, we have expected ice age in 1000 or 2000 years, though it is now delayed. But from this point, after the Industrial Revolution, it has constantly grown up. The temperature increased since then. That's why it is not a part of the Milanković cycle. So that that theory is ruled off. That is cancelled.
Okay.
Let me just check. Okay, so you're only here. Uh, Also, some basic questions are on ice age, how the glaciations in the higher latitude started. Uh, that is actually through colder summer or weaker solar radiation. Because if summer is cold, then winter it will get more scope to spread the ice, and the next summer it will spread more slowly. It will cover a lot of parts in the northern hemisphere, and eventually it will also affect the southern hemisphere. Second question is the last few ice ages still 1 million years. Okay, the time period 1 lakh years for the last few ice ages, but the strongest solar radiation cycle, that is basically the precision of Earth, is 21,000 years. So explain the difference. Yeah, of course, it is not linear. Depends on the internal conditions on Earth. Solar radiation has to decrease below threshold value for this. Yeah. Another thing is there. Before that, before 1 million years, the ice ages did occur in the periods of 41,000 or so, 41,000 years or so. That happened actually because the eccentricity was quite high at that point of time, and it somehow helped the effect of the obliquity and the precision to take into account. Now the effect is not uh, that linear.
How can we calculate the eccentricity before at 1 lakh years time period? How is
Uh,
it done?
how to calculate? Mm, I think one thing is possible, that it is a very well studied problem. Actually, in classical mechanics, most of the problems are quite neatly solved. So, you know, we actually know when the solar eclipse in the next 1 lakh year will happen. We know that. So,
Okay.
astronomers and astrophysicists, whatever, whatever, scientists, they have calculated this very precisely, because we mostly know the mass of the planets, the distance of the planets quite well. And using
Okay.
computers, we can easily predict, because it is a classical mechanical problem. In classical mechanical problem, unless something comes out from the distant galaxy or in the interstellar space, the things will mostly be predictable.
Yeah.
So, given three bodies, you can suppose you have a classic textbook problem. Two bodies are moving, they have distance r between them. After some time, what will happen to the distance? You can calculate that. You have Newton's law of motion, you have the calculus. So, using that, you can precisely calculate that. So, we
Okay.
have data for, let's say, 100 years. So, we know the pattern in what way the Earth has moved. We know the pattern of different planets, let's say Mars, Venus, Jupiter, Saturn, whatever effects can be counted for the change of eccentricity or precision or orbital obliquity, those type of things. So once we know those factors and we have some data for 100 years, or for astronomy, it is still even longer. People started astronomy since long. So they have the data. That's why they can calculate that. That's what my understanding tells. I don't know the perfect answer for, or I have not gone through the question before, but I think that is just a gift of classical mechanics and astronomical calculation, that we can precisely predict what is the current eccentricity, what is the time period, what will it be, those type of things. I don't know. I mean, we were actually human, actually human. actually has been quite good in doing the calculations of the astronomy. Since long they predicted eclipses or the transitions of different planets across sun, this type of
Okay.
things. So I think we
I
have
think there is
started.
also value for eccentricity. Is it E is equal to C by A or something like that for ellipse?
No, I mean that is there. I mean that you can calculate. Given the velocity, given the distance, you can calculate. I mean, for no, you can cal. Are you talking about the current eccentricity? Current eccentricity can be easily calculated.
Yeah,
It
but
is basically root over 1 minus b square by a square, where b is the semi-minor axis, a is the semi-major axis.
okay,
So we
okay,
know the value of b, let's say 14, okay, let's say 0.147 billion kilometer, right? Or let's say the highest value is 0.152 billion kilometer. Using those values, you can just calculate the eccentricity, current eccentricity of Earth, 1 minus b square by a square root over that.
okay, okay.
But for finding past eccentricity and the time period, future eccentricity, I think they also take into account the attributes of different planets and also the sun,
Moon.
which contributes majorly to the change of the
Okay.
eccentricity. And for one thing I can tell for orbital obliquity or axiality, the moon plays a stabilizing role. If the moon were not there, then our orbital tilt would have fluctuated more.
Okay.
Yeah, so a basic question. What happens to the delta 18O values in the ice cores during ice ages? So yeah, delta 18O values, the more 18 oxygen as it is heavier will be dropped to the ocean basins. That's why in the ice cores, the smaller value uh, will be there. Ocean has higher ice ocean. I mean, basically the ice extent in the world is higher. That's why in the ice core the value is smaller. That's how it is. I think you have a question on that where they have just presented the delta 18O in the ice cores, and from there they have asked for a few questions.
Okay. Yeah.
Okay, well, that is a classical calculation. I have not done that, but that is a result. How the eccentricity can change the solar annual mean radiation. It is only dependent on eccentricity. So S is some constant divided by 1 minus E square root of that. Currently, we know the value of eccentricity for the Earth. Okay. Oh, okay, okay. Here I have just tried to get the data from this website, and they presented nice columnar data. So just to play with the data, how we can play with the data, how we can interpret those things for them. Here, there's the total data. The first panel is about the time period, not time period, time before present in kilo years. So it is 5,000 kilo years, means 5 million years before present. So that is the value of delta 18. No, it is slowly decreasing. Actually, it means that from past it has increased in the present. Now this is a very complicated time series. What our goal is to find the time periods associated to that. So we need
Okay.
to take a Fourier transform of that. Using the Fourier transform, we can find the dominant powers, dominant frequencies. Dominant frequencies means frequencies which have the higher powers. So that is a small portion of the time series from 0 to 1000 kilo years. Now looking at this graph, you can say that it is mostly repeating after 100 kilo years. So you can see a what else?
Yes.
Periodicity here. After that, you know, after that another. So in 400 kilo years, it has repeated 4 times. So in 100 kilo years, it will repeat 1 time. So the time period is basically 100 kilo years. That is the dominant
Yes.
time period. Okay.
Yes.
So that is by eye, but actually it is not always possible to tell by eye because there are very complicated time series which you basically won't understand what is there. That's why we need to do the very beautiful tool by the Fourier. There is a Fourier transform, Fourier analysis, extracting the frequencies from the time series. So, so may I know your discipline in which you are studying?
I'm not actually studying as such.
Okay, that's fine. No, I was just thinking if I give some analogy to a particular field, or I will try to do that, but it's fine. So, yeah, and here is the last time series which is presented from 3000 to 4500 years below present. Here we'll not see that 100-year cycles dominantly. Of course, it has lower power, so we'll see that. But we can see, I think we cannot see that. But there are smaller frequencies which dominate, actually smaller time periods but higher frequencies. So the time period is smaller and the frequency is higher. Now we will take a Fourier transform of that first first column. That will give you the as powers associated with that for this case. You can see strong power in the 40 kiloyear time period. You can see another strongest power is in the 100 kiloyear time period. That is what the strongest power of ice age lies. That is where the strongest power of ice age lies. And the second strongest power is in the 40 kiloyear. It has some power in the 60, uh, 3, 4, let's say, and some power in the close to 90 kiloyears. Now, if you take the power spectrum of the second uh, second column and first row, then we will see that there is a strong power associated with the 100 kiloyear time period. That's what we have experienced in the past, that there is a very strong power in the 100 kiloyear time period. Another power lies in the 40 kiloyear time period, which aligns with the Milanković cycle of the obliquity. Now, for the third time series, that is far below present, 3000, that is basically 3 million years to 4.5 million years before present. Here we can see a dominant power lies in the 61. At least, actually, it should be close to 45 or so. Maybe some problem is there, but it is not in the 100 kiloyear time period. So the 100 kiloyear or 1 million year time period has very low power. And this, sorry, 100 kiloyear means 1 lakh. 1 lakh year has very low power in this particular time interval. Just to do the Fourier analysis and finding the frequency. You can do it for any time series. So for understanding time series, we need to do this type of operations. On this, we can resolve it by eyes. But it is better to always do the time series. Okay. Question is out there. This topic I have to cover, that is about stochastic forcing. I will go there. Yes. Okay, so at least I think it should be in the record, so I will just continue. So stochastic forcing, it is a non-linear behavior of the system in which the typo, so this change of the output is not proportional to the change of input. So in linear systems, the change of output is actually related to the change of input. Suppose we are giving some periodic forcing to a spring, then uh, the periodicity of which it oscillates, if the force is given, is same as the forcing frequency, because it is a linear system. Now, due to some cause, the system is non-linear, or the response of the system to the forcing is not linear, then the time period or the response time of the system will also change. It will not be equal to the frequency of the forcing. There are many instances in the uh, geo, uh, geological context. Uh, let's say the very basic example can include the temperature of a deeper ocean. Let's say there is temperature change in the atmosphere, but the temperature change will not be evident in the ocean, especially at the deeper layers. It will be evident after maybe multiple times of the time scale of the change of the temperature in the atmosphere. And this is because the temperature in the ocean is governed by different processes, which are rather complicated and which take a lot of time. For example, the thermohaline circulation, it takes a lot of time, the order of 1,000 years to complete the whole path. We can also see nonlinear phenomena in atmosphere. Suppose there is some sudden change of pressure or temperature. So the response might not be exactly linear. There are associated factors. There might be change of wind directions. There might be change of wind speed. There might be rainfall, and also the change of heating, the temperature, this type of thing. And they will eventually act to control the or balance the pressure. So it will not be exactly periodic as will be the forcing. There are different waves in the atmosphere which are periodic, but the atmosphere doesn't believe in the periodicity or doesn't always accept the periods. So we need to decompose different phenomena in the atmosphere, and then we can attribute one particular phenomena to a particular period or event with particular periodicity. So that is uh, that is an example of stochastic forcing. Also, if there is noise in the system, then it will not exactly act as the forcing frequency. If the noise is there, then it will be partially controlled by the noise also. And due to the noise, the equilibrium states uh, will be achieved at different times compared to the forcing timing. That's why the frequency of the forcing might not be equal to the frequency of the response. Now here, the stochastic resonance is considered in order to explain the phenomena of ice ages due to the Milanković cycle. Now, Milanković cycle is there, but the periodicity somehow doesn't match with the periodicity of the temperature. So there are some mismatches. Now, how can you explain this? Of course, there is something internal happening which is contributing to the irregular periodicity of the Milanković cycle, or not Milanković cycle, but irregular periodicity of the ice age. Milanković cycle is a, let's say, well-defined phenomena. So it has certain documented value of periodicity, of obliquity, eccentricity, or the precision. But the combined effect is not that simple. It also deals with the noise present in the earth. So that might not always lead to the exact periodicity of the ices as the Milanković cycles, because a simple example is that not at every minima, or not at every minima of the ice age, Milanković cycle, the ice age will be achieved, because it has to reach certain threshold value and start the ice albedo feedback. After that, it can continue. Now, but if we have some prescribed forcing with the Milanković cycle, then we can derive the time period of the recent ICGs, which are about 1 million, up to 1 million year before present, with the time periodicity of 1 lakh years or 10 to the power 5 years. We can try to explain that. Okay, so I will just continue from here. Let's check the recording is doing fine. Oh, that's good. Okay, so starting from the basic energy balance context. So we have the heat capacity C of Earth and the change of temperature with respect to time that should be equal to the net radiation received. S by 4 times 1 minus alpha t, where alpha is the albedo, and sigma times epsilon t to the power 4. Sigma is the Stephen Boltzmann constant. Epsilon is the emissivity of Earth. We have done this exercise. We know the typical values, and from there we can establish some equilibrium temperature, making T by T capital T by D small t equals to 0. Of course, the
Sorry, but my internet connection went out. I'm sorry about that.
yes. Are you able to hear now?
Yeah, I'm able to hear. I had logged in through the mobile, so that's how I'm doing right now. So
Okay, so you can see the screen, right?
yes.
Okay, so I was just talking about the stochastic forcing, and basically, yeah, I have just talked about those things because it was just a reading type of thing. But the due to the non-linearity, even if the forcing is well periodic, the system can behave in a non-linear way, and the periodicity that emerges from the system can be non-linear. That might be due to the internal noise of the system that can cause the system to behave differently compared to the given forcing. So, for example, let's think about the solar forcing. The sun exactly repeats, or the solar insolation exactly repeats after 1 year. So today 6th March, exactly at 2027 6th March, the Earth to Sun distance, the radiation amount from Sun to Earth will be exactly equal. But the weather will not be exactly equal. There will be some variations. What is the cause? That is due to internal variability that we take as noise. Whatever we cannot explain, we can take it as noise. So this thing will affect the state of Earth in the next 1 year. Uh, so these forcings actually are effective in controlling the ice edges and also the modulating the effect of the Milanković cycles. That's why we are trying to build some theory with this stochastic forcing. So again, we are dealing with a simple model. C times the change of the temperature is equal to the insolation, solar insolation times the 1 minus albedo. So whatever energy is received, shortwave radiation they call, and minus the outgoing radiation, they also call it long wave radiation. Sigma is the Stephen Boltzmann constant, epsilon is the emissivity. When both are balanced, then there will not be any change in the temperature. And alpha is also a function of T. Alpha is actually higher for lower temperature and lower for higher temperature. So there are two equilibria for this system.
Yeah,
One,
Liu's model.
huh?
You Liu model was there regarding it.
Yeah, Liu's model was good, right? So it will give two equilibria, and in which in between there will be unstable point. In the two sides, it will be stable. Just an example. Now, if somehow due to forcing one can shift one point to the another, then the system will try to stay close to that particular stable equilibrium. But again, if forcing is applied, then sorry, not forcing. Again, if noise is applied, then it might come down to that particular the first equilibrium point. In that way, it will not always follow the forcing, whatever is given, and can lead to rapid changes in the equilibrium points, and also rapid changes in attaining those equilibrium points that might not respect the frequency of the forcing that is given. That can give us some answer to the Milanković cycle. So in the Milanković cycle, it is considered as a weak forcing, and that weak forcing will not actually be able to always command the earth to go according to its forcing. That's why it will not always bring ice edges to the earth. The internal noises are also there that will combinedly act with the Milanković cycle, and that will decide whether there will be ice edge or not.
Okay.
So yeah, that is the basic concept, that is equilibrium. But here we will add some uh, um, terms here. We will add noise terms here and amplitude terms here. Okay. Okay, just a diagram how to explain the stochastic resonance. So there are two equilibrium points. Let's say A and C. Now, if a particle is here at C and it is given small forcing, then it cannot get out of that particular value C. It will stay close to here and it will respect the forcing. It will follow the forcing. But if due to some noise it is actually jolted and it is spread into, it is actually transported into the sea, into this region, then it will attain the equilibrium A. And then it will try to follow the forcing. But again, if it is given another type of noise, it can go to C. So that's how the switch between the two equilibria that might lead to some other periodicity apart from the forcing period or forcing frequency. Now, in climate model, I think you have the questions in the assignment using this type of model, and they have identified the equilibrium points. They have introduced some forcing. Using that, they have asked you to derive some simple questions like derive the time period for one case, derive the time period for another case. This type of things. It is very easy to answer. We will just try to take one simpler example and see the basic notion of it. We consider the simple equation dx dt is equal to 5x minus x2. Now, if you take dx dt equals to 0, it will have two roots. One root is, so actually three roots. One root is x equals to 0. Another two roots are x equals to root over 5 plus minus root over 5. Okay. Now x equals to 0 will be unstable point and x equals to plus minus root over 5 will both be stable points. So the system will anyhow try to go to that stable equilibrium point if it is given normal condition. So if we apply weak periodic forcing, the system will stay close to one equilibrium point depending on where the initial condition is and oscillate according to the forcing frequency because it has nothing else to go, nowhere else to go. And if there is strong noise imposed, then the system can be influenced to go from one equilibrium to another. Now, the time period of oscillation might not match the forcing frequency because the time period has another factor which has the switching frequency between one stable equilibrium to another. That can be considered as another time period. In our ice age case, one can be considered as ice covered, another can be considered as ice free domain. That's how we both are stable actually in Earth system case. Now, of course, as x equals to 0 is a unstable point, it will stay close. It will never reach the unstable point because it is an unstable point. Then it will actually be shifted to one of the stable equilibrium points. Now we can draw a simple analogy with the interglacial and glacial periods. With that, we apply some periodic forcing, which is sine times sine of 2 pi by Tp. Tp is the time period, T subscript P, times T. T is the time. And minus x cube, just with the equation, we have added two terms. 5x minus x cube was always there. So 5x minus x cube, these two terms are there. In addition to that, we included that periodic forcing and this beta times, b times eta of T, which is noise term, which has the noise from minus 0.5 to 0.5. So it follows a uniform distribution. That is, it will take uniformly values between 0.5 to minus 0.5, and we'll impose that in our equation. Now, this is the equation. Then we will just see a few results in the equation, and then we will try to draw an analogy between the equation and our Earth system in a simple manner. So that is what we will do in the next few minutes. Okay, so is the system clear? We're dealing with that system.
It's fine.
So yeah, so let me just ask. T Prabha Varik has just joined, so just ask. I will explain it once more because can you hear me, Yuti Prabha Varik? Shall I repeat the system once, because we will just be showing some results from the system, so it is better to go through the system once. It is a very simple system. Shall I go through once, or I can continue?
Yes, sir, you can continue.
I can continue, or I will. Okay, I'm continuing. So basically, I'm just repeating. So we will just solving the equation, differential equation. Dx dt is 5x minus x cube, and in general case, it has two equilibria points, plus minus root 5. One is both are stable, and the unstable point is x equals to 0. Okay, so in normal case, it will try to stay close to the stable equilibria. And now, to see the effect of forcing and periodic forcing and noise, we have introduced the term of sine of 2 pi divided by t subscript pt. Tp here is 2.5 second. Actually, we have taken that value, and b times eta of t, that is the noise term. Now we will see the effects of those terms into the equation. Just we will solve the equation, nothing else. So may I know whether you can computationally solve differential equations using some method, Euler or RK4 method, this type of methods?
Laplace transform can be used, right? I'm not sure.
Laplace transform. Oh, I don't know about the Laplace transform, but for solving differential equation, you can use. I'm just talking about computationally solving, not analytically.
Oh, okay. I think characteristic equation can be written and then solved for ordinary differential equation. I'm not sure about this
No,
case though.
you're telling right, but it is for solving analytically. You can do it in pen and paper, but
Oh, okay. Okay, then we can actually bring down one. Okay, we need to look at the differential equation, right? I think integrating factor.
yes. Yeah, I mean, whatever you are saying is analytically solving the equation. That is completely fine. But computational solution is even simpler. So you take some initial value, given the initial value, you take the value, and then just find dx. Is that right hand side times dt? And the right hand side can be complicated
Oh,
also, but just multiply it with gt and increment the value of x. You have got from x1 you have got x2, from x2 you will get x3, and just go on. So that is very simple. Okay. And for finding
okay.
the term, you can uh, use basically finding the dx or delta x term. You can use Euler's method, RK4 method, or many techniques in the computational physics to analyze those things computationally. I mean, that's how we did it. That's why I just mentioned. Anyways, so with this, in the first case, we have taken 2 points very close to the unstable equilibrium. Oh, so, ah, so in the first case, we have actually taken two unstable equilibrium. One is little above zero, one is little below zero. So the value which is above 0, there is no noise imposed in this case. So the value which is little above 0 will try to reach its equilibrium point of plus root over 5, which is close to 2.35 or so. And the value which is little below 0 will try to its closest equilibrium, stable equilibrium point. This is minus 2.35 or so. And it will be oscillating. Just note the time period. It oscillates every 2.5 seconds because the time period we have imposed is 2.5. So here you can see one peak. Here also you can see another peak, and it will go on. So the time period of the fluctuation is exactly equal to the time period of the forcing. So in the forcing equation we just mentioned the Tp, and it is giving exactly the time period of Tp. Now we will increase the noise. Okay. Now we will increase the value of B to 100. Instead of 0, we will make B 100. Now what it has done is it has retained the time period, though it is not very visible through this graph. But if you take Fourier transform, we will get the time period. But it has also introduced lower time periods or higher frequencies in between them. So it has introduced some new frequencies into those cases. Now we can also increase the noise mode. Now see the difference. In that case, it stays in the stable, for first stable or the higher stable point for some good amount of time. Let's say for 7.5 seconds or so. Then it suddenly goes down and it stays in the second stable point or the lower stable point for 4.5 or 5 seconds or so. Then it again goes there and comes down for with a period of 2.5 seconds. And then it again tries to stay in the lower point for more than 5 seconds. So the periodicity is actually not exactly equal to the forcing frequency. That's how the effect of noise comes or takes the control over the frequency of the oscillation. So once you introduce high noise, then it will try to impact the system a lot, and it will switch the equilibria and introduce some new periodicity. You can think it as ice free or ice age, whatever. You can think the other point as the another one, ice age or ice free, and using that in between you can see the intermediate points, and you can think like that. So it is an analogy to explain the ice ages. Though we have imposed 2.5 seconds of time period, we're getting time period much longer than this. Sometimes it is shorter, but sometimes it is really longer. So that is one way to explain the 1 lakh year time period of the ice age using stochastic noise or stochastic or random forcing. That is called the stochastic resonance. Now, if you increase the noise even more, then the changes will be drastical or very irregular. So we will get rapid fluctuations between these two states. As the noise is high, it will rapidly fluctuate between upper and lower equilibrium points. So that's how it will lose the effect of the weak forcing on the system. The noise will take over the system, I think. Yeah. So any questions regarding this slow transition or this transition from weak noise to strong noise? I would be happy to discuss.
Stronger noise doesn't mean that the Holocene period will be low. The time to next ice age will be lower time period because there are fluctuation. Is it like that or
So your question is stronger noise will mean the fluctuation is higher.
the time period to the next ice age is
Oh,
lower
okay,
level?
okay, okay, okay. Yes, actually, stronger noise can do two things. It is actually stochastic phenomena. So one thing, of course, stronger noise can bring down to the lower temperature very quickly also, but it might also stay in the upper range. it depends on the particular noise. So in this case, in that particular instance, we generated some random numbers and it behaved like that. So there are periods of longer and shorter transition. For this, consider this time period. During this time period, the whole thing was above zero. But just after that, it quickly transitioned between zero to, sorry, between below zero or negative value to positive value. So it will be more fluctuating. That's what we can say. But deterministically, we
Okay.
cannot tell. But it will, in general, it will be more fluctuating. That is true. Uh, Now, in Earth's case, the problem is we are just applying one constant forcing that is not giving uniform noise, but it is actually
Very good.
increased forcing. So that is the just increasing the temperature. Is
Okay.
the problem.
So CO2 can it be considered as noise? Is it no? Isn't it noise?
I think CO2 should be considered as forcing, not noise,
Noise. Okay. Okay. Okay.
because it has an effect with particular direction. It will always increase the temperature. It is not that it will
Ah.
decrease the temperature, but noise can increase or decrease the temperature. Now this is just a model. We
What?
don't know whether the exactly the noises what the exactly the noises are. We're just trying to model that if we add this noise, we will be able to get longer period of colder ice age and warmer ice free time. That is it. With Milanković cycles.
o- Okay.
So yeah,
Thank you.
so some basic questions we actually have discussed those things. So how the ice age might not exactly follow the periodicity of the Milanković cycle due to stochastic resonance. What is the response of the system when the noise is weak? When the noise is weak, then system will try to follow the forcing. What are the differences in ice ages from one Y is missing, a million years before present, and from 1 million years before present to 2.5 million years before present. So that is basically the difference in the eccentricity of Earth. During that period, the eccentricity is low. So somehow the ice ages have the time periods, dominant time period in 1 lakh years, and from 1 million year before present to 2.5 million year before present, the ice age has time periods with strong power in the 41,000 year cycle. How can you ensure that the global warming is not due to natural variation of the Earth? Just look at this particular graph and we can see that the global warming is not the natural variation due to Milanković cycle of the natural variation of Earth. And we have not also seen this type of change since the last 10,000 years, the Holocene. So these are the things. Okay, so that I had to present today. Any questions? If you have any questions, I will be happy to answer.
No, everything is clear.
Okay, the assignment, you just do it. I think the assignment questions, it might use some um, illustrative terms, but in basic, just go through the assignment. The questions are simple enough and you will be able to answer with your basic understanding. I will just ask Yuki Prabha, do you have any questions?
Namaskar.
Okay. Okay, so see that there is no doubts. Then we can conclude today's session. We will meet the next week. Okay.
Okay. Thank you.
Thank you.